Foxbot, and welcome back to calculus. Woo! So in this video, I'm going to show you at least the introduction on how to do calculus integrals. Yeah, super fun. So just to cover really quickly what integrals are. So when you have a function, let's say for example my function looks like that. Whoa, so crazy. We're going to call this function of x, and then you have x here, and so then you have your f of x here. So what an integral does is it allows us to calculate the area underneath our curve, and an undefined integral is going to be, from negative infinity to infinity. So it's going to most likely be a function of x, but a definite or defined integral is going to be from a specific point, so like x equals 0 to x equals 1. And then what you're doing when you integrate, I'm going to draw this line a little higher up to our curve, is you are basically adding up little chunks, and then you're multiplying them together. So you're going for each x, figuring out what that value is at that point, and then you multiply basically like the x values by the function values, just like you would if you had a square of length a. I guess if it's a square, both sides are a, so a and a, then your area is a squared, or a times a. So basically what you're doing the exact same thing here, except instead of a number, you have a curve. Okay, so let me erase that. So you know how I'm always like, don't memorize anything, understand it. So there is a little bit of memorization in doing mathematics, basically just in the way that when we learn language, like English or Mandarin or Spanish or whatever, we have to memorize words as well as how words fit together. And so math is a lot like that. If you understand the rules, it makes it a lot easier to memorize, because then it's, you can fit them into place within those rules, but there is still a little bit of memorization. So integration, same sort of thing. A lot of it is just like knowing the rules. So let's start simple. The sign for the integral is this like elongated S, which is pretty cute. And then you have a function here. We'll start simple. So we'll say x. And then you're integrating with respect to a specific variable. So for example, if instead of dx it was dy, then effectively your x becomes a constant, like a number, because you're not integrating with respect to x. So this is really important because this tells you how to take the integral. Basically that tells you, if you look at the curve again, that tells you what that variable is on the bottom. Okay, so this is an indefinite integral, so it's implied it's negative infinity to infinity. And basically what that means is when you do the integral, you kind of leave it as is, I suppose. So I'm going to put this back to dx. And so with integration, kind of like how division is the opposite of multiplication, integration is the opposite of derivation. We're taking the derivative. So the opposite of this, if I go backwards, you have to think, okay, if I were to take the derivative of something, what would I be taking the derivative of for me to just get x? And since I've done a lot of calculus, I can tell you right off the top of my head, it's 1/2 x squared. And because this is an indefinite integral, I always have to add a constant at the end. And the reason why is because we can check our work, huzzah, by taking the derivative of this. And if I were to do that, so I would take the derivative with respect to x of 1/2 x squared plus c dx equals, so again, this operator acts on this to take the derivative, and that gives me the 2 comes down, it multiplies by 1/2, so that gives me x. The derivative of a constant is 0, so I get x plus 0, which is just x. Ta-da! Yay, we did it right. So that's what's super cool about integration, is that we can always check our work. Yay. Okay, so what do I get if I have a definite integral? So say from 0 to 1, because I'm lazy, I'll keep the numbers easy. So again, you get the same thing, 1/2 x. And if you want, you can add the c. I think it is important to keep that in mind, and so it's just a good habit to get into, but as we'll see in a second, the c actually cancels out. And so the notation for a definite integral is that you take this function from 0 to 1, and so just like you're finding the distance between a line, again on our curve, if we have our funny curve here, you're basically finding the difference between these 2 points, where x is 1 here and 0 here. So you would do 1 minus 0. And so what that looks like is you just plug in these numbers for x, and you calculate the result of this function. So that looks like this. So you have 1/2 from x is 1, so 1/2 times 1 plus c. And then you minus, again, just like you would do if you were to take if you were to find like the distance between 2 points. So minus 1/2 times x is 0 plus c. And then if we simplify, this becomes 1/2 plus c minus 0 minus c. Boom! C's cancel. Huzzah! Told you they would. And then you just get 1/2. So the definite integral of x dx from 0 to 1 is 1/2. And so that's actually the area under the function. If x is 1, from 0 to 1, would just be a straight line. And if you want to check my work, you totally should. So basically what that looks like is a triangle with bottom length 1, and I'll let you figure out what the hypotenuse and the other side is, and then you can calculate the area and tell me if that is the same or not. Okay, so let's do a couple of other examples. Actually, I kind of want to go back to this. What happens if you have x dy? What? That's super weird. And we'll do an indefinite integral. Oh my gosh, I'm in chalk everywhere. Okay, so if you're taking the integral of x with respect to y, that basically means that x is a constant from the perspective of y. So you can treat that kind of like a constant. So think about if that was a number, how would you do the integral? Well, just like you would, you'd think about what's the derivative of a constant? What would you have to get just a constant? So you would have x times y, and then what do I need at the end? A plus c. So then it would just be xy plus c. Boom, done, no problem. And so in this instance, even though x it looks like a variable, you treat it like a constant. So yeah, so the integral of like 2 dx is just going to be 2x plus c. So for exponents, so let's say you have x squared dx, you basically do the same thing that I did previously, where you kind of reverse the derivative. So this would be 1/3 x cubed plus c. And then you check your work again by taking the derivative d dx of 1/3 x cubed. The 3 comes down, it cancels out with the third, you get x squared, the c goes away. Boom, no problem. Okay, let's do something a little more complicated. So let's do x squared plus 1 dx. Oh my gosh, what? So you treat the two parts kind of separately. You could also write this actually as the integral of x squared dx plus the integral of 1 dx, and you get the same thing. And so if you want to do that, I'll give you a second. Okay, so then you get 1/3 x cubed plus x plus, well, I guess this would be plus c, plus x plus c2. And since these constants, you don't know them, we're just putting them in there to let the viewer know that, hey, there might be a constant here and we're not really sure. Since they're both unknown constants, but they're both going to be numbers, you can combine them to just give you like a large C or something. Or if you want, you could call that C3. And how you would determine that constant is you would need what are called boundary conditions. So basically you would need specific points on that curve. Let's say you're given a point 3, 2 that works. You would just plug in those values to calculate for the constant. Yeah, cool. Okay, so let's generalize this a little bit because I like making rules general. So if you have a function that's dependent on x, whoa, that was silly. My chalk's getting kind of small. So function x, and you're taking the derivative with respect to dx, you basically can think about this as like, this is f prime of x, and then you always add a constant. Okay, so those are kind of the basic rules. It does get a little bit more complicated. So say, for example, you have a function f of x times a function g of x, dx. This you would need to do integration by parts to basically separate the two functions out. And that is a formula that you would memorize at a certain point. It's been a while since I've done this, so hold on. I think it's f of x times the integral of g of x dx minus, oh my gosh, f prime of x. Okay, yeah, I don't remember, so don't quote me on that one. I would be curious though, someone should look it up and leave it in the comments, or I'll probably put it in the comments or something. Okay, so yeah, doing integrals is the opposite of taking the derivative. It can be fairly straightforward to do a single function, but it can get more and more complicated when you have more complex functions. When you get really high into calculus, you'll start seeing things like this. Oh my gosh! The integral with respect to 2 variables? What? It's okay, don't worry too much. Basically what you would do is you treat it like order of operations, and you just do one at a time. So you would take the derivative of both of these functions with respect to x, and then you would take the derivative, so actually it should be like this. There should be 2 integral signs in front. That looks like a dollar sign. And so this one would be for x, and then this one would be for y. So it can take some space on your paper, but just go slow, step by step, and you got it, no problem. Alright, so I'll leave it there for now. I recommend you looking up the rules for integration and just do some practice problems and get all comfy, and then eventually you'll be like, oh, no problem, no big deal. They'll just naturally sink into your brain. Alright. So please let me know if you have any questions about anything that I showed you here, or if there are topics in math or calculus or physics, engineering, whatever that you would like me to cover. Thank you very much for watching, and I'll see you next time. Bye!